Alright, so there are two main things that you're going to learn today. Number one, we did our stuff yesterday, and I told you the shape of the distribution of samples. I just said, boom, let's put all these things in a normal shape. And you just said, okay, and then we went on with it. You can't just say, assume it's normal shape. There actually are rules or conditions that you have to check to see if the normal model applies. Okay, that's critical. So we're going to learn those today. First thing is, vocabulary-wise, you need to know by name what the central limit theorem is and what it says. Alright? First off, I'm not going to tell you the whole thing yet. I'm going to tell you first off, the central limit theorem is a theorem that is about the shape of the distribution. And we're going to determine if our distribution behaves normally, like the normal model. Okay, so that's our ultimate goal, so that then we can do z-score stuff and all that other. Here are the rules that you have to check to see if it behaves normally. The first rule is you have to make sure that your sample has been taken randomly. That's critical because in the first part of the school year, what does randomness help us to do? Cut out the bias. Very good. So randomness is important so it's not biased and so that we get a representative sample from the population. So I want to do these conditions for M&M lab yesterday. So let's say you would do this. You would say random. That's the first thing we have to check. And would you say that it's reasonable that your bag of M&Ms is a representative sample, that it's the M&Ms are in there randomly, and that they are representative of the whole population of M&Ms? I think so. I mean, we're not experts in it, but that's a reasonable assumption I think we can make. So we're going to put our bag of M&Ms seems random and representative of all M&Ms. Okay, that's the first assumption you have to check. Second, this idea of independence. Independence is critical because we have to come to the conclusion that when I look at Zach's bag of M&Ms and I examine the proportion of blue M&Ms he has in them, then I go and look at Byron's 50 M&Ms and I look at his bag of M&Ms. Do I think that his proportion of blue M&Ms is going to be affected by the amount of blue M&Ms that Zach had in his bag? Why do you think that his blue M&Ms is probably 24% chance still of being 24% or 24% blue, and is the same as Zach's? Why has Byron's not changed? They are sampled from all along the lines. What did you say? They are two different bags. They are independent samples. So what Zach gets is not affecting the rate at which the blue M&Ms appear in Byron's bag. That's critical. One of the main reasons that's happening is because the M&Ms that they are drawn from is like, a billion gajillion. So 50 little M&Ms is not going to change the proportion of 24% blue M&Ms in the population. Okay? So one little bag, one little sample is not affecting the overall probability. This is the mathematical stipulation that we follow. So for our M&Ms, we would say, all right, let's check the independent condition. It would say our sample of 50 is less than 10%, and it can be equal to, less than or equal to, 10% of all M&Ms. So if our sample is small enough that it's less than 10% of the population, then picking out one sample is not affecting the probability of another sample. That's what this is saying. And just for fun, well, you know what? I'm afraid it might mess actually with this thing since my computer's messing up. I'm going to wait to show you that M&M video here in a little bit. All right. So for independence, we want to make sure that it's small enough, but it needs to be large enough, so it has to be just right. Not too big, but not too small. It has to be large enough to be representative. Yes.
When you did like the big division, and you put it out for us, would that not be independent from each one? Because since you're getting rid of any names that could maybe belong to someone else.
That is true if my 24% rate was just, like I had already counted, and my population was just that bag of M&Ms. But since that's still coming from all M&Ms, and that's from that whole overall rate, then that's not going to be changing it as well. Okay, so to the large enough. There are two large enough conditions. If you are a mean problem, if you have means and averages, then your sample size has to be greater than or equal to 30. Some textbooks say greater than or equal to 40, but the AP exam and different studies and guides and whatever, they'll see that you have one of the standardized rules and they're good and they'll go with it. For us, was our M&M bag considered a mean problem, a distribution of means? They were percentages. So what we had was a sampling distribution not filled with means, like average times to run a mile. We were filled with proportions of blue M&Ms in our sample. So we had proportion problems yesterday, and here are the large enough situation for a proportion, and so that is this. In order to be large enough, there needs to be at least 10 successes, and this is a mess up right here. At least 10 failures. So at least 10. The NP is like the successes. So in our situation, how many blue M&Ms you'd have, and then the NQ is the other stuff. By the way, some textbooks, and then just because it's shorter, I'm going to be using Q instead of 1 minus P. Okay, Q is the other part, P is the proportion you want, Q is the other part, so it's the figures. Okay, so let's do this for ours. Yesterday, we want to see if our sample was large enough. So here we go. Our sample sizes were 50. The proportion of blue M&Ms that the M&Ms company told us, the Mars company told us, was 24. That is 12. Is that greater than or equal to 10? Yes. So that's considered large enough for that one. Let's check the failures, which actually is even larger. The rest of the sample, it's the other 38. So that also is large enough. So our samples yesterday were considered representative. They were considered independent from each other and not change the probability of success, and they were large enough. So therefore, our sampling distribution yesterday of our proportions of blue M&Ms followed the normal curve, if I had put them all in our picture. Oh, by the way, one last thing. There actually was thought put into you having 50 as your sample size, because another part of the lab yesterday was the orange M&Ms, and the orange M&M proportion was 0.2. So in order for that to be large enough, I had to do 50 times 0.2 in order for that to be greater than or equal to 10, because 50 times 0.2 is 10. So on other labs that I had gotten off the internet, they actually used size 40 for the sample size, but I found that wasn't large enough because it didn't meet that particular criteria. So I changed to 50 for you so that we had met the conditions. All right. Now, the next thing is this actual central limit idea. The This is huge. Okay? About to be like super totally excited that this idea is huge and major. Here's what it says, and then I'm going to show you a demonstration of it. The central limit theorem says if your sample size is sufficiently large enough, then the sampling distribution, meaning this thing down here, will be approximated by the normal curve. And here's the oh my goodness, major part. Even if the parent population, the distribution of the entire population, is not itself normal. Okay, so that may seem a little abstract, so I'm going to show you a picture of this situation. So here we go. Actually, I have a demonstration. Let's do this. All right. Do I have any runners? Who are my runners in here that don't have cross-country people or anything? Oh yeah, we got Colby. He's a cross-country guy. You do my cross-country guy? Okay. So let's say that this. See, look at this distribution. Is this normal shaped of any? No. Would I be comfortable with making any type of proportion or prediction as far as probability that something's landing in this here? No, because I would have to use calculus. To get the size of these areas since it's not normally shaped. See, the good thing about the normal model is that calculus is done for you. It's already computed into your z-scores and all that kind of stuff. But this is not. So here we go. Let's pretend like this is Colby's times of the miles that he has run. So like he's done a mile and then he's recorded the time his whole life, or maybe even just since middle school. Let's pretend like, say, he used to not be so fast before he got started. So this is kind of his, this is an individual time of one of his 1 mile runs. And this is another time. So these are individual pieces of data in here. Now in the summer he started training, so a lot of his times were centered around this section. But then once we got to school and we are now training for our track meets and whatever, all that kind of whatever. So now we got things more located in this general vicinity. Now we're going to pretend like this is 0, that it's actually scooted up to a reasonable time frame. Okay, so now he's trained, he's prepared for his meets, he's more in this general vicinity for his times.
Where's the time?
Oh, I'm sorry. This would be like the time in minutes, but I don't know the scale of what it is. So this would be the time in minutes to run a mile. And then these are like frequency, how many he has done. No, I'm saying sometime, like he has done a collection of events that have kind of had this type of time frame. And then whenever he was in training, here, I don't know, and then here's when he's at his peak performance, and so he's got his time centered in this section. Oh, is that hard to understand? Okay, so that's what's going on. This would be considered the parent population. This is full of individual times. We're going to call this the parent. See, you get me off my game here. P-A-R-E-N-T, parent population, because these are all individual values. These are not averages. Okay, so now here's what this computer module is, or module, applet, whatever, is going to demonstrate for you. I'm about to start pushing some buttons, and it's going to drop down 5 individual, randomly selected times that Colby had recorded in running his mile. So it's going to drop down 5 times, and then it's going to average those times, and it will drop down the average of these 5 selected times and put it here. So down here, we will end up with a collection of averages. We'll end up with a collection of average of 5 times. An average of 5 times. And we're going to start building a histogram with averages of 5 times. This is called your sampling distribution because it is made up of sample means. All right. So here we go. Let me actually erase this part here. And let's put this into action. So here comes the first 5. Randomly chosen 5. There's the average of them. Here comes 5 more. Randomly chosen 5 and the average of them. And so on. So let me do this a few times. So every time it is picking a sample of 5. Now, we know in the central limit theorem that's not very large, right? It's only 5. What's it supposed to be for means? To be large enough. 30. What happens is, because this is a sample of only 5, it's going to actually take a long time for you to see the pattern appear, which is good that we got this animation. I can do a lot of the samples at one time. If n was greater than or equal to 30, then the pattern would appear faster and then more appropriately. So, but just for this simulation, they do just 5 individual pieces and drop down. So now I'm going to start doing more than one trial at a time. I'm going to do 5 sets of 5. Here we go. There's 5 sets of 5. There's another 5 sets. See, these are stacking on top because we're getting more in this area. So look, I'm starting. So now, again, because this sample is so small. Now it looked like it just jumps down. Well, that's because of the scale over here on the side. They changed it. So I'm going to do 1,000 at a time to speed this up. It's taking forever, again, because the sample size is only 5 instead of 30 or more. Look. And if I do 10,000, I mean, look at how close this is getting to the normal approximation. So listen to what this central limit theorem says. It says, if n is sufficiently large, then regardless of the shape of the population, when you take sufficiently large samples, they will drop down and the sampling distribution can be approximated by the normal curve. That's huge, because that now means you can investigate anything. You can go collect data and you don't know what shape it's going to be in the population. But if you do this and you take your samples, then you can approximate your information with the normal curve from the samples. Well, I mean, you take some samples, or even actually you can make this approximation from one sample, and we'll get to that later. But that's in theory what's happening. Okay, so that's the big deal of the central limit theorem. All right, next idea for today is what happens to the standard deviation as n increases. So if you turn over to the back, I have some pictures for you, and let's look at these. This first picture has a sample size of 1. If the sample size is 1, that's all the individual pieces of data. That's like every single run that somebody has run. So this is considered the parent population. All right, because its sample size is of 1. And the standard deviation of this population is 2.007. All right, now let's look over here. This second picture is samples of size 2. So they randomly took 2 pieces of data, they averaged them, and they dropped them down. So this is a sampling distribution of samples of size 2. So it's getting, a little further away from being so skewed. As we drop down samples of size 4, it's now becoming less skewed. Samples of size 9, samples of size 16, 25, 40, and 100. Okay. That's what we just talked about. Central limit theorem says as your samples get larger, your data will behave more normally. Here's the deal. And by the way, I'm sure that Byron will catch this. This is supposed to be 120, 240, and 360. Okay? So just kind of catch it before you do find out. It's all right. That's good that you're catching things. So here's the deal. Let's look at what's happening to the standard deviation on this page. Because the standard deviation has to do with the variability. How consistent is the data? That's important. You want things to be consistent. So look, originally, the standard deviation is 2.007. Look at the next one. What has happened to the standard deviation? It has gotten smaller. If it's smaller, your data is already more consistent. Look here at this one. The standard deviation is 1. It is now half as much as it was up here. And here's why. Are you ready? The standard deviation of this sampling distribution is the standard deviation of the population divided by the square root of n. Look, that's 2.007 divided by the square root of 4. So the standard deviation has been cut in half because of the square root of 4. Okay? So my variability is now smaller. You can see, look at the scales on the x-axis. It's gone from going out to 15 to now it's going out to 10, or less. Okay? So I'm getting more consistent, less variability. These are good things. So here, with an n of 9, my standard deviation of the sampling distribution would be 2.007 divided by the square root of 9. So I'm dividing by 3. So the standard deviation is now cut to 1/3 of its original standard deviation. All right, and so you can see all the way down to here, the standard deviation of this sampling distribution is the original one divided by the square root of 100. It is now 1/10 of the original standard deviation. Very consistent, very much condensed. That's a good thing. So, in summary, what we find is that as your sample size gets larger, the standard deviation of your sampling distribution gets what? Smaller. Very good. Why? Because what's happening? Say like from here to here, what's happening? We are getting more precise. That's an effect. But why are we getting more precise? Look, I want you to reference. We're adding more and more people, so what's happening to this value down here? The what is getting larger? The denominator. Very good. So it's getting more and more precise. The standard deviation is getting smaller because the denominator gets larger, and so that's making the value smaller. For example, if you have 1/10 versus 1/100, this has a bigger denominator and it has a smaller value. Okay, same thing. All right. So in summary, we had three major things today, I guess, actually, instead of 2. Conditions that make something normal. Understanding that the central limit theorem is just this crazy, crazy important thing, because regardless of what the parent population looks like, you can end up with a sampling distribution that behaves normally. Yes? I can't. Yeah, I don't have that ability. Oh, yeah, I can't. Oh, yeah. But you know what, though? Hold on a second. So there's been something with that I've tried before. Hold on, let me move that out. Yes. Yeah.
It's like absolutely no effects.
Okay. So that's what you were doing, because I was about to totally, go all ballistic on you. I was about to, totally mark up my 6th period stuff, and y'all are already behind. Okay. Let me stop this. Oh, and by the way, in summary, again, the final idea is that as your sample size goes up, your standard deviation and your variation in the sampling distribution goes down. Okay, done. Now, I want to do some of your homework with you. We'll actually go to that. Get to your homework. Part 2. This was something I did not have the luxury of doing with you yesterday. I like to do one of these problems so you can see exactly what I want you to make sure you include. And I have time to do that with you today, so here we go. Number 9 is actually the first one here. So based on past experience, a bank believes that 7% of the people who receive loans will not make payments on time. The bank has recently approved 200 loans. All right. So let's determine if the conditions are met for this to be considered behaving normally, or normal distribution. Okay, so I want you to get real and tell me if it's behaving normally. This is for you to remember the 3 conditions you think. Get real. Come on. So what's the first condition we are checking? Thank you. Okay. So, question. It doesn't say that these loans were taken randomly. So, do you think it's reasonable to assume that those loans are representative of all the loans that the bank makes? You think it's really not? Okay, well then that could be something that we call into question. But for the benefits of continuing with this course, otherwise we'll just say no on all of it and stop. Oh, and by the way, I can tell you that on like a free response, pretty much you're never going to go, no, the conditions aren't met, so I will stop now. Okay, you're pretty much going to have to get to the conclusion that you might say, well, I'm a little concerned about this randomness feature and if this is really representative, but I will continue with caution, and then you go through the motions, okay? But anyway, so we are going to assume, and you know what happens if you assume, but we're going to do that here, that the 200 loans are representative of all the loans at that bank. You know, they do have standards and such, and so they can't just be handing out loans willy-nilly. They have to meet a certain criteria. Okay, what's the I remind you that the condition is? Independent. Okay. So, we're seeing if 200, the rate of the faulty loans or people that default on their loan is 7% of 200, that's overall. Is one set of 200 going to be about the same as the other set of 200 as far as the rate of default? Okay, so it should be similar to our M&Ms, but remember mathematically the way we're kind of clarifying that is we are saying N, which is 200, is probably less than 10% of all of their loans that they hand out at that bank. Most banks, that's probably the case. All right, and what's our last condition that we check? Large enough, okay? So now, is this a mean problem for large enough or a proportion problem for large enough? It is the proportion problem for large enough, and that's at least 10 successes or failures. So that's your NP and your NQ have to be greater than or equal to 10. So we go like this. 200 times 0.07, which is the P, is 14. And that is greater than or equal to 10, so that condition is met. And here we say 200 times the other 93% is the rest of the loans. So that's the 186 of them, because 14 of them are going to default on average. And so 186, well, that is greater than 10 also. So we have kind of clarified that these are the conditions that need to be met. Some of those are assumed, so we're going to go ahead and assume that and say normal model applies. Okay, so since normal model applies, let's go also using the mean and standard deviation of stuff to do predictions. So, what's the mean and standard deviation for the proportion of clients in this group of 200 that may default on their loan? Or not make their payments on a timely manner, whatever. So, this is yesterday's stuff. The mean of the sampling distribution is going to be what? P, which is 7%, okay? And then the next thing, the standard deviation for the sampling distribution is, that's your square root of PQ over N. Okay, which is 0.01804, which is 1.804%. No, I don't think so. Yes. It's always an ongoing battle. Make me check. More up that. Okay, so next question. What's the probability that the 200 loans that you selected are going to have 10% of these clients default or higher? Actually, over 10% of the clients are going to default. So let's kind of draw a picture, and then I want to go back to what does this P hat represent. This is something that you guys are kind of like struggling with defining, and we got to fix that. You need to be able to tell me what each P hat is representing. So first, our picture has samples in it that are proportions. What do each one of these P hat proportions represent? Not an individual piece of data. Each P hat it's a sample, but how do I know the number value of each P hat? It's a what? Not mean. Closer. Get closer. It's not an average. It's a, thank you. It is a proportion. Okay, P hats are proportion. And each one of these proportions is the proportion of what? Of what sample? How big is this sample? The proportion of 200 loans whose clients default or don't make payments in a timely manner, whatever, however you can most succinctly say that. Each P hat is, oh man, time's up. Okay, but you get that. I'll let you do the M&Ms here in a minute. Go, tell me. Okay, so let's finish this. So our problem is wondering, okay, if we have an average of 7% people that default on their loan, then what's the proportion or what's the probability that over 10% will default on the loan? So, in other words, what's the probability that you get one of these P hats, this sample, in this area? Okay, and so of course what you're going to be doing is your z-score information. So you're going to get your z-score, see how far away your 10% is from what's expected on average with this standard deviation, and that is 1.66. So right there, I'm already knowing that this is not too strange of an event. From this, I know that this 10%, if I got a sample that's right at 10%, I could have gotten that just because of sampling variability. It's not necessarily because I am having a higher rate of default. So then, of course, we're going to do our norm CDF on that. And we've got 1.64 to 1.66 to 99. That is 4.85%. So if I was to write this with the correct notation, I am saying the probability that I get a sample proportion that has greater than 10% default is 4.85%. So now, put this two words, and you say the probability that a sample of 200 loans from this bank has over 10% default actually I kind of messed up on the equal to there, is 4.85%. Okay, so that's how you're doing that. You're going to finish the rest of those, and that's your Chapter 18 homework part 2.